Hello everyone, welcome once again to my channel and welcome to this video. So in my last few videos, mostly I have talked about graphics algorithms, Linux things like how does containers work in Linux, how processes are forked in Linux and things like that. But in this video, I am going to do something different. I am going to play with hardware, and what I am going to do is I am going to create a very tiny, minimalistic, simple game console from scratch. We'll be using a microcontroller, we'll be using a tiny screen, a tiny mono display screen, some buttons here and there, and yep, that's it. With that, we are going to create a very simplistic game console. We will be building two games, the classic Space Invaders and the classic Pong, simple versions of those, not with all the features, but simple versions of Space Invader and Pong, and we will try to run those on our console, right? So that's what we are going to do, and this won't be a single video, of course, or else it will be just way too long. So I'm going to split this entire thing into multiple videos. Hopefully it will turn out to be a cool series. Let's see what the end thing will look like. Is something like this. So this is what the end console will be looking like. Very simplistic, nothing fancy. So yeah, we'll also be going to use some 3D printing. So the outer covering of this console is 3D printed, and to keep it simple, I have created a very basic cover for this, for the circuit, and hence I have left the front side exposed. As you can see, we'll be using a tiny screen. Inside we'll be using Raspberry Pi pico microcontroller and a few switches. These are just push to on switches and a tiny off on switch. So if I switch it on, it will look something like this. So we have got two games built into it. One is Pong and another one is Space Invader, as I mentioned. Let's play Space Invader, and there is a selector button, so I can select this and it says press fire. This is the fire button, and here we can move left and right, and we can shoot, right? And the enemies, the aliens, can also shoot back at us. And if I check Pong, if I show Pong, then let's select Pong, let's press fire, and again it's a very simplistic version of Pong, right? So this is what we are going to build in this video series entirely from scratch. Let's get started. Okay, so before we start to build anything, let's find out what are the things we will be needing, right? So the first thing we need to decide is the hardware on which our console software is going to run, or basically our games are going to run. So what's the hardware? So we have got quite a few options for this. We could either go with something like SOC module, the SOCs provided by Espressif. They have got multiple series of SOC modules with various variants, with different variants, of course. Like we have got the ESP-P series, S series, and so many. So a SOC is a module which has got multiple things packed into it. It's the short for system on chip. So for example, if we check the ESP32P series, it has got a high performance MCU with RISC-V dual core and single core microprocessors. It has got voice processing capability. It includes, of course, GPIO pins and so many things. We have also got SOCs with Wi-Fi capability built in, right? And MCU plus Wi-Fi. So MCU is basically microcontroller unit. One of the other options we have is Raspberry Pi Pico microcontroller from Raspberry Pi. It's pretty cheap, and it comes in two variants, one with Wi-Fi support and the other without Wi-Fi support. We could go with this, or maybe we could go with something like the Arduino Nano microcontroller. This can also serve our purpose. This is also pretty cool. One thing to mention is that when you are developing on a breadboard, I would suggest taking the ones which has got header pins. By header pins, I mean the pins, the legs that come out of these connection points, because otherwise you will have a hard time connecting them to your peripherals. With header pins or leg pins, you can simply plug it into your breadboard and make your connections very easily. When you put it on something like a Vero board or a PCB0 board, at that time, since you will be soldering your connection points to your peripherals, that time you don't need the leg pins. So for that purpose, you can use a microcontroller which doesn't have leg pins, but for breadboard you should always get one which has got pins, because otherwise you can't put it into your breadboard. Right, so these are a few options. There are tons and tons of microcontroller options, SOC options. Microprocessor, something like a full-fledged Raspberry Pi Zero or something like that, is just too much of an overkill for this tiny simplistic project. So I would suggest against doing that. One of my primary targets while building this is to keep the cost of building it as simple as possible, right? So for this case, for my project, I'm going forward with Raspberry Pi Pico microcontroller. The non-Wi-Fi version is really cheap, so I chose that. Now the other primary peripheral we need for our handheld console is a display, a tiny display, and a monochrome display is perfectly fine for this because we won't be using colors. So one very cool monochrome display and one very popular and easily available monochrome display is the SSD1306 OLED I2C display. Let me quickly browse it. So yeah, this is the SSD1306 I2C OLED display. You can find it easily on Amazon. I'm going to use the 0.96-inch OLED module. As you can see, it supports I2C serial communication. I2C is a peripheral communication interface, with which it's an interface by which you can let your peripherals communicate with your MCU or microcontroller unit, and it's a master-slave protocol wherein your development board or your Pi Pico is the master, and you can configure your display as a slave. In that way, the master, which is the Pi Pico, will send commands to your display, and the display will act accordingly. All right. If I zoom one of these pictures, it mostly comes with 4 pins. So one is the ground pin, which you will be connecting to the ground of your entire system. One with the VCC. The VCC is what will power the display, and you have got SDA and SCL for communication purpose. We'll be using this. I would suggest, if you are going to use a breadboard, get one with leg pins, and when you put it on your Vero board or PCB0 board, you can either cut off the leg pins or get one without the leg pins. So personally, I will have 2 setups. One is on my breadboard. It's like a staging setup where I'll be testing and doing everything, doing the basic development, and I have another setup where I'll create the circuitry on a Vero board, the one which I just showed in the beginning of the video, and there I used a Vero board to create the entire circuit and put it inside the cover, right? That's our display sorted. So I'm going with the SSD1306 I2C OLED display, and the other thing that we need is some jumper wires. Now for testing on breadboard, I'll be using jumper wires, which will have those pin-like terminals to inject in your breadboard. When you're putting it on a Vero board for soldering purposes, or when you are actually soldering your wires with the microcontroller or the peripherals, you can use any 22 gauge wire. Those are also easily available on Amazon. So this is the one that I purchased, and this works pretty good. And for the switch, you can use any two leg pin switch. 2 leg pin switches are very easy to deal with. I use both 4 pin as well as 2 pin switches. 4 pin switches, I initially started with 4 pin switches when testing on breadboard, but when putting in my actual circuit for the console, I switched to 2 pin switches. 2 pin switches are easy to deal with. You just have to deal with 2 leg pins, that's it, but you can go with either of them. There are a number of options depending on how much tactile feedback you want while playing. You can select a switch depending on that. So that's for our switches, and that's pretty much it. For breadboard, you can use any breadboard. I prefer a long rectangular breadboard. You can use the mini breadboard ones, like the one that's shown in this picture. Like, you also get mini breadboards like this. I usually prefer the longer ones because it gives me enough room to do different tests and trials. So I prefer a longer rectangular one. So yes, that's all the things that we'll be requiring. Now let's start with our initial setup and see how we can use the Raspberry Pi Pico. Okay, so now let's see how to write code for the Raspberry Pi Pico, what environment we are going to use and all those kind of things. So when it comes to writing code for Raspberry Pi Pico, there are quite a few options. The official method of developing for Raspberry Pi Pico is using something called MicroPython. It is a version of Python which is used for hardware programming. With it, you can do things like accessing the GPIO pins, accessing peripherals and all those kind of things. MicroPython has recently become quite popular and it supports other platforms as well. For example, it supports ESP32 as well by Espressif. The other way you can code for the Raspberry Pi Pico is the Raspberry Pi CSDK that's provided by the Raspberry Pi Foundation. That is also there. The other very popular way of programming for the Raspberry Pi Pico is the Arduino IDE. Yes, so the Arduino IDE also supports your Raspberry Pi Pico as well. So if you want to use Arduino IDE, which is what we are also going to use in this series, either you can download their official native IDE, which is this one, right? The suggested version right now is Arduino 2.x. You can go for this one, or the other thing that you can do is set up Arduino IDE via an integrate Arduino IDE with an extension in VS Code, and that is pretty much what I am going to do in this series. So VS Code comes with an Arduino extension. It's a third-party extension which you can install on VS Code and you can set it up. And there is also another option if you don't want to use any integrated environment, that is, you don't want to integrate the Arduino development ecosystem with any of the editors. You can also use the Arduino CLI directly from your terminal. You can use a simple editor to just write your code and then compile it and upload it using the Arduino CLI. One cool thing about the Arduino ecosystem is it's very easy to switch from the Arduino IDE, the Arduino native IDE, to the VS Code extension, or from these two to the Arduino CLI. The reason is both the VS Code extension and the Arduino native IDE, both of these uses the Arduino CLI behind the scenes. So whatever you do from the front end gets translated to Arduino CLI commands and gets executed on the CLI. Which also means if you want to use any external library, if you install that library using the Arduino CLI, it will be available to be used both from the VS Code extension and from the Arduino native IDE. Also, if you install something from the Arduino native IDE or in VS Code extension, it can be used from the other side. That's an advantage. The other advantage you get if you use the Arduino IDE is the plethora of libraries that's already available for the Arduino ecosystem. You can use all of those. If a version is available for Raspberry Pi Pico, like all might not be supported, but you will find a lot of libraries to be used at the end of the day. Now, I won't dig into details of how to set up your VS Code with this extension because there are already a number of articles on internet on how to do it. The one which I followed and I found very useful is this article. It explains in great details how to install VS Code, how to set up the extension, how to configure your board, your extension for your board, how to set up, how to install external libraries and all those kind of things. So it's a pretty cool article. I will link this article in the description of this video. Do check this out. I have already installed this extension in VS Code and it's working fine. So if you install this, the things that you will find in your VS Code is these buttons over here. One is used to upload your code directly from the IDE to the development board, and it will run it as well there. And also an option to just compile the code, that's also there to debug your code. Once you have plugged in your Raspberry Pi Pico, what you need to do is select your board here. I have already selected Raspberry Pi Pico, and as you can see it has populated all the configuration here. The second thing you need to do is, I'm right now on Linux, Ubuntu, and once you plug in your board to your laptop, a serial port will appear under your /devices. So let's have a look. So after plugging in your board, if you do a ls on /dev, you will see this communication port, which is a serial port, TTY ACM0. Mostly on Linux it appears as ACM0. On Windows it appears as, I believe, COM3, but I'm not sure. You can use it on macOS as well, but we'll stick to Linux in this series. Once this port appears, you need to select this port here, right? You need to select it here, which I've already done. And that's pretty much it. Now you can start writing code in your VS Code and upload it directly from here to your board. So a little bit about the Arduino language. It's an extension of your normal C++ programming language, and which means you can also write native C code for your Arduino. Your project should have at least one .ini file, which will act as the entry point for your application. This is the one from which you will be doing the upload, and it can, just like a normal C++ program or a C program, it can include header files. So you can also have your code inside a normal .c file, create a header file for that .c file and include that header file in your .ini file, and you will be able to access your C code. So once this gets compiled and the final build is produced, all your C code will be linked together along with your .ini file, right? So yeah, that's pretty cool. That's pretty much it for setting it up. Next, we will see how we can access our display and do some drawing or draw shapes, basic shapes, lines on our SSD1306 OLED I2C display module. So we will see that, but before we can write code, let's look at a basic pin connection of how to connect your display with your Raspberry Pi Pico so that we can use I2C interface to draw things on your screen, right? So let's have a look at that. Okay, so now let's look at the basic circuit diagram for connecting your display to your Raspberry Pi Pico so that we can write some code on it. So what we would essentially do here is, as I mentioned before, the display module that we are going to use, SSD1306, it has got 4 pins. 1 pin, 2, 3, 4. Now this is ground. This pin will be connected to the ground of your system. You can connect it to one of the grounds of the Raspberry Pi Pico. What usually people do is all the grounds in your entire project is shorted and it's connected to one ground. That's pretty much how ground connection is done. So the other is VDD. This is the pin by which the SSD1306 display module will be powered. So you can connect this to the V out of your Raspberry Pi so that it receives the power to switch it on. This pin is the SDA pin, and this is the SCK. We don't have to right now go into the details of what is SCK and what is SDA, but this is required for the I2C communication. This is how information will be exchanged between the master and the slave. So as I mentioned, I2C is a master slave protocol, wherein in this case the master will be a Raspberry Pi Pico and this will act as the slave. So now let's bring in our Pi Pico. So this is the USB. This is the USB connection. This is the USB port. So usually on Raspberry Pi Pico, the SCL pin is at GPIO pin number 5, and the SDA pin is at GPIO. Sorry, it's at GPIO 4. Mostly it's the 6th and the 7th pin. If you start counting the pins from the top with the first pin marked as 1, mostly 4th is the pin number 6 and 5th is the pin number 7. It might vary, but it's mostly this way. SCK is also sometimes called SCL on certain display modules. We'll be connecting SCK to GPIO 5 and SDA to GPIO 4, and ground will be connected to. So if I open the pin diagram, so when working with the Raspberry Pi Pico or any microcontroller or chip or any hardware chip, the datasheet and the pin diagram is your best friend. The GPIO 4 is the 6th pin and GPIO 5 is the 7th pin, and you can use this ground, like the pin number 38 ground pin, and for V out, which is 3 volt, you can 3.3 volt, you can use the pin number. If you count on this side, this is 1 2 3 4 5, the 5th pin on the right side of the controller, which is also the 36th pin mentioned over here. So what we are going to do is, let's say this is the third pin, which is ground, and this is the fifth pin, which is 3v3, right? So now what we are going to do on our breadboard is we are going to connect ground with Raspberry Pi Pico's ground, VDD with the 3-volt supply, the SDA with the GPIO pin 4, and SCK with GPIO 5. And that's our simplistic circuit to power our display and to write things or draw shapes on our display using our Raspberry Pi Pico. And finally we'll connect this to our laptop USB, right? So this is a simple pin diagram for allowing our Raspberry Pi Pico to control our display. Okay, so now let's write some code. We'll start with importing or including some header files. Let's quickly do that. So I'm using Adadruit SSD1306 library, which will allow me to access the external display module very easily. That's there. Those are the header files. Let's define two macros, one for screen width. Since I'm using the 0.96 inch display module, my width will be 128 pixel wide, and I'll have 128 columns in simple words, and the height will be 64, so it's 128 pixels wide and 64 rows or 64 pixels in length or height. Then what we need to do is we need to initialize our Adafruit library. Let's call it disp as of now, and let's do screen width, and let's pass screen width and screen height. And then as usual, an Arduino project should have at least these two functions. In this tiny example, we won't be using the loop function. We'll do everything in setup itself. So first we'll begin serial communication. That's why we'll do serial.begin. We will use a baud rate of 115.200. Then we will just check if we are able to, our display is initialized fine. We'll just see if our display is working fine. For that, what we'll do is we will pass this constant, and we will pass the address of our display. So it is both of these are constant, and you don't have to think much about this. This is usually 0x3c, and yeah, that's it. If we find that our display is not initialized correctly, we print a error message, SSD1306 allocation failed. And we simply loop forever. Now the SSD1306 comes with a opening banner, and usually what we do is we will just spit it out once on the screen, and immediately we will clear the screen so that no one sees it. It's disp dot clear display. Right, but since I want you all to show what the banner looks like when you boot up Adafruit's SSD1306 display for the first time, what I'll do is I'll put a delay of 1 second. Yeah, 1 second. And then what we'll do is let's say first draw a line. Display, sorry, this dot line, draw line, and let's draw a line from the screen. The screen coordinates here works in the same way as we have seen in other graphics windows or in computer graphics. That is, the top left corner is 0, 0, the positive x is along the right hand side, the positive y is along the downward side. So if you go down, y increases. If you go if you go right, x increases. Also, it means that since we are beginning from 0th pixel, the far rightmost pixel will be 127 and the bottommost pixel will be 63. So it's 0 to 127 and 0 to 63. Okay, so let's draw a line from horizontal line from 0, 2 to, let's say, 63, like the rightmost pixel, 2. So it will be a straight horizontal line, right? And also let's draw another rectangle from 0, let's say 10 to, not 0, let's make it 10, 10 to say 20, 20. And we'll have to say the color as well. SSD1306 inverse. Inverse means if the default color of your screen is black, this will be white, right? So it's a pretty easy way to specify the color of whatever filled shapes you are making. And what we cannot forget to do is then do a display or disk dot display. And now what we'll do is we will hit upload. My pico is connected to my laptop right now, and I hit upload, and you see, and as you can see, we got a error. So let's see, why did we get an error? Alright, we need to mention the color here as well. SSD1306 inverse. Let's try to upload once again. Oh, my bad. It will be disk. So the code got uploaded, and let's see how it looks on my physical device, on my physical board. As you can see, this is how it looks on my physical board. Apologies if the camera is shaky, because I'm using my mobile camera to record this, to film this. So yeah, if you see the connections, I have my ground, my VDD, SCK and SDA, and these are connected to the appropriate pins on the pico. This is the GPIO 4, GPIO 5, this is ground, and this is 3.3 volt, right? And as you can see, it printed the horizontal line from 0, 2 to 63,2, and my bad, it shouldn't have been 63, it should have been 127 for the rightmost edge. But yeah, you get the point. It printed from 0 to 63, which is kind of the midpoint, and it also printed a rectangle, actually a square because it's 10 by 10. So it started from 10,10 and it went to 20,20 on this board, right? So yeah, that's pretty simple to draw shapes on Adafruit's SSD1306. So you can not only draw lines and rectangles, you can also draw unfilled rectangles, which is just the rectangle without any color inside. You can draw rectangles, rounded rectangles. You can draw a pixel and so many things. One very easy way to find out what all you can do is just go inside the definition, and you can find all the functions over here inside Adafruit gfx.cpp. So how it is communicating with your display is via the I2C interface protocol, or it's also called I2C in some places. So now let's see how we can attach a button to this Raspberry Pi Pico, and how we can see the state of the button, whether the button is pressed or whether the button is released, and how using that button we can make updates to what is drawn on that screen in real time. So that's how we will control our characters. Like, that's how we will control the Space Invader cannon and the Pong paddles. Okay, so now let's see how we can use a button or a push to on button with a Raspberry Pi Pico. So how we can use a button which is connected to Raspberry Pi Pico. But before that, we need to understand the fundamentals of how a button works. The button will be connected to a GPIO pin of the Raspberry Pi Pico, right? And the other end will be connected to the ground. One more thing we need to understand is what is pull-up configuration or what is pull-up register configuration in the Raspberry Pi Pico. For that, so let's first try to understand that. Let's say in our case, we will connect our button to the GPIO 6 of the Raspberry Pi Pico, and we'll be using one of the ground pins. Let's first understand what is pull-up configuration. So all the GPIO pins of Raspberry Pi Pico by default is in pull-up configuration, which means by default all of them will exhibit a steady state of logical 1 or logical high voltage. So let's see how it looks. Let's say this is our MCU Pico, right? This is GPIO 5 and this is VCC. What's VCC? VCC is the voltage that we are supplying to the Raspberry Pi Pico, like the source voltage. So now what happens is, this pin is connected directly to VCC by some resistor R1, right? So by default the voltage that we will be getting here is VCC, so here it will be VCC as well, and the work of this resistor is to provide a stable voltage at this, otherwise it will be in a floating state. If we would remove this resistor from here and directly connect this pin to VCC, we would get a floating voltage over here, which we don't want. So in digital electronics or in digital circuitry, we want a logical 1 or a logical 0, that is a stable voltage. So hence right now we will get VCC over here. What we will do is we will connect this pin to a button. So this is a button, and the other end of the button will be connected to ground. So this is the symbol for ground. And now what will happen is, once we close the button, VCC will be connected to ground and we will get a logical 0 over here. So that's pretty much how a button works in pull-up configuration state. If the pin is in a pull-up configuration state, it means by default it will have a logical 1 over here. Whenever we close the switch, we are completing the circuit, VCC is getting connected to ground and we'll get a logical 0 over here. So this is what we would need to keep in mind. Whenever we are pressing a button and the circuit gets closed, what the expected value at the button pin should be 0. Again, if we would have used a pull down configuration state, then it would mean that via some resistor the button pin would already be connected to ground. By closing the circuit, we would get a logical 1 at the button pin, right? So let's see how this looks in code. So first we'll define a, let's define a constant here. First we'll define a constant here. So first we'll define a constant for our button pin. So const in pin button equal to 6. Then what we'll do is we will set up the pin mode over here. Pin mode, pin button input pull up, right? And then what we will do is we will inside our loop. So now we will use the loop. So at a particular frequency, which is the frequency of your microcontroller, all the instructions within loop gets run continuously in a cycle. So whatever you write in this loop, it will get executed again and again repeatedly over and over at a certain frequency. So inside loop, what we want to always check is we first want to get the button state, and in the how we get the button state is we do a digital read on pin button, and for now let's just print out what, like print it to our device output what we get the button state as, right? So yeah, that's pretty much it. So what did we do here? We first defined a constant for our pin button, which is 6, GPIO 6. We then set up the pin mode as input pull up for pull up configuration, and then inside loop we want to continuously check the state of the button. For that we do a digital read pin button and we spit out the pin state or the button state in the console output, right, or the device output. Let's see how this works. Let me bring in my breadboard, and the other thing that we will do now is, okay, let me first deploy it to the device. So it is compiling now and it's done. So let's open our device output, which will be cat, we will just cat the device file, cat dev tty acm0, and you can see the state of the button by default is 1, which makes sense because it's in pull-up configuration. So always by default we will get a logical 1 at the output. Now let's look at our circuit once. So here's the circuit once again, and let me just pull aside the wire. So I'm in the process of creating a common ground. So this pin I'm using as the ground pin, and for the ground pin I'm using the ground pin I have chosen over here is the pin 13, the 13th pin. So the 13th pin I have connected it to this socket of the breadboard, which makes this entire row or this entire row as ground, and so this becomes ground. And I have done another connection. So this leg of the button I have connected it to ground, right, as we discussed. And now this blue wire I have connected it to GPIO 6. So this is GPIO 6, right? So the GPIO 6 I have connected it to what the other leg of the button, right? So the button, as we discussed, is connected now to GPIO 6, and this is the old code that we had written, which prints a square and a line. Now let's see how the output changes. So whenever I press the button, you see on the screen it becomes, the state of the button becomes 0. If I press it and hold it, it's continuously 0, right? We will also see later how we can change this behavior in, like, let's say when we are shooting, or like when we are shooting bullets from a gun, we might not want to release a continuous stream of bullets when we keep the button pressed. So we will see how we can change this behavior later via code, where we can get rid of this continuous button pressed effect, but at a software level, not at a hardware level. But as of now, what I wanted to show you all is that how we can capture the button state change, and how pressing the button changes the output to 0 from 1. Now next, what we'll try to do is will be something more interesting. We will try to use multiple buttons to control the movement of an object on the screen. Just like how we control our characters or an object in game, we will try to move it in 4 directions: left, right, up and down, via 4 buttons. So each button will be responsible for one direction. So let's see how we can do that. So now that we know how a button works and how we can capture the button state when someone presses the button, let's put it to some use. Now we will see how we can control something on the screen by pressing the buttons, or rather I should say how we can use the button to do something interactive on the screen. What we are going to do is we are going to create a tiny object on the screen, maybe a tiny rectangle, and we will try to move it around in the screen. So we will try to mimic the left, right, up and down arrow keys, and we will use 4 buttons instead of 1, and we will use 1 button to move the object left, 1 to move it right, 1 to up, 1 to move it up, and 1 to move it down, right? And we will do some very basic boundary checks so that the object doesn't fly out of the screen. It always remains within the screen so that we can see it. Let's try to do that. So for that, what I'm going to do is, firstly I'm going to get rid of these random drawings that initially I showed how to access our screen. So let's remove these. And one more thing I'll do is, let's change this name disp to display. It makes more sense that way, I believe. And let's here, I believe that's it. And yeah, now the first thing that I'm going to do is I'm going to add some more buttons, and I'll also add them to my circuit as well, but let's make the code changes. So some more constants. Let's rename this to left button. Then let's add a right button, view video, and equal to 7, and I have used up button to be 9, and I have used down button to be 8, right? And now what I'm going to do is the same thing pretty much. I'm going to put these as I'm going to set their mode to pull up, and the last one, which is down button, to pull up. Next I will create a tiny struct over here, and I will just type def it. I will call it player T, because the object is kind of like our player, and which will be able to control, right? So that's why I'll call it player type. And let's give it some properties. Width. So again, our player will be a rectangle, right? So it will have a width and a height. Speed, and this will be like a constant number by which its position will get incremented or decremented to move the player around the screen. And then we will have pause X, pause Y, and that's it. And I will also define a player of type player T. We'll call it player. I'll give it a width of 8, height of 4, speed of 1, and when the screen boots up, the player should appear in the middle of the screen. So that's why screen width by 2 and screen height by 2. Okay, so now what I will do here is, rather than reading the button state in the loop function, we will to some extent try to mimic what a traditional game loop does. So usually what a game loop does is, a game loop primarily calls to certain key functions. One of them is process input, another is update, which updates your entire scene, your entire world, and final function call is render, which spits out everything to your screen, that is, it updates your screen. So here we will keep it simple. We will create a function which processes our input and updates process input and updates the player variables or the player properties. So let's do that. So what we will do here is we will do int move left, and here we will store the state of left button, right will have the state of the right button, up for up button, down is for, okay, looks like I made a typo there, for down button, right? And next let's check if any of these buttons have been pressed and update the player properties accordingly. So if move left equal to 0, which means if it has been pressed, and player dot pos x is greater than 0, we will basically move the player towards left hand side, and in order to move to it towards left hand side, you need to subtract the player speed from its position x property. Remember, like when you reduce the when you want to go towards left, you need to decrement its x position or x coordinate, and if you want to move the player right, you need to increment its x coordinate. And same for your up and down movement. If you want to move up, you need to reduce the y coordinate, and if you want to move down, you need to increase the y coordinate, because the origin of our screen is towards the top left corner of the screen, right? So we will do player dot pos x minus equal to player dot speed. One more thing we should be discussing here is the origin of, so every object in a world or in a game world or in a scene, they also have a origin, right? So around which the entire body of the object is fixated. Sometimes it's the geometric center of the object, sometimes it's the top left corner, and like it depends on you which point in the object you want to consider to be its origin. Usually it's the geometric center, but in this case my player is a simple rectangle, right? So to keep things simple, what I'm going to do is I'm going to consider its origin to be the top left corner of the rectangle. So that top left corner of the rectangle will be its pos x comma pos y, right? So if I want to explain it in a bit more detailed manner, what I'm saying is, let's say this is our rectangle, okay, this is our screen, this is our screen's origin. So what I'm saying is that any object in a game world, it also has got a local origin around which basically determines where the object is located. So in this case, so one very common position to consider as origin is sometimes the geometric center of the body, sometimes this is the one. So let's not term it as x comma y or ox comma oy. Sometimes it's the geometric center of the body. So in this case, what I want to do is, this top left corner will be the origin of this body, and so this is basically your pos x and pos y. So whenever we want to move the rectangle towards right, we will increment pos x. Whenever we want to move it right, we will decrement pos x. If we want to move the body up, we will decrease pos y because origin is 0, 0 over top left corner, and if we want to move the body down, we will increment pos y. Now coming to very simple boundary checks, we don't want this body to go out of the screen. So then if it keeps coming this way, there will be a time when it will just go out of the screen and only this much will be visible, and we don't want it, right? So the constraint will be pos. Whenever we are updating the pos x value, pos x should always be greater than 0. Only then we will decrement its value, and it should, and pos. So when this body comes to the rightmost edge, it will look something like this, right? It will look something like this. So if we try to calculate the point coordinate of this point, if this is your pos, if this is our pos x and pos y, this point over here will be pos x plus the width of the body, comma, pos y. Similarly, if we want to check what happens when the body goes at the topmost position, so let's say here our constant will be pos y should always be greater than 0 if we want to move the body up so that it doesn't go out of the screen. So it will be pos x plus y, and when we are incrementing the value of pos x, we always want to make sure that pos x plus w is always less than the screen width, the width of the screen, or else this edge will go out of the screen. Similarly, when the body moves up, we want to make sure pos y is always greater than 0 before decrementing the value of y. Similarly, when it moves down, let's say this is the position of the body when it's in the bottommost edge of the screen, and again once again this is pos x comma pos y. So the coordinate of this point will be pos x comma pos y plus, so this point's coordinate will be pos x comma pos y plus screen height. So we would always want to make sure that pos y plus h is always less than screen height. Right? So these are our constants, or also these are our very simple boundary check conditions, so that our character or the movable object always remains within the visible screen. So let's do the same thing in our code. What we can do here is, so if pos x is greater than 0, player dot pos x equal to minus equal to player dot speed. If move right equal to 0, which means someone has pressed the right button, and player dot pos x plus player dot width is less than screen width, only then we move the player towards right. So we do player dot speed. Now let's do the same thing for up and down. If move up equal to 0 and player dot pos y is greater than 0, only then player dot pos y minus equal to player dot pos player dot speed, and if move up and if move down equal to 0 and player dot pos y is less than screen height, only then what we'll do is player dot pos y plus equal to player dot speed. As simple as that. So if we are going up, we check if pos y is greater than 0. If we are going down, we check that pos y, okay, pos y plus player dot height is less than screen height, and only then we update it. Cool. So the other thing, or the other function, so that's our input processing and updating the player object. And now we want to make our render function. So what render function will do? Render function will simply draw the player on screen. So for that, what we can do is display dot fill rect player dot pos x, the top left corner of the rectangle, player dot pos y, player dot width, player dot height, and the color. And we want to show it on screen, so for that we will do display dot display. But we need to do one more thing, and that is, so this render will be called by our main loop, right? So every time we will try to draw this thing on the screen. Before render starts drawing the updated position of our object, we need to clear whatever is present on the screen, or else it will, the different positions of the player, or the updated position of the player and the existing position of the player will get superimposed on each other, and we will get a very horrible looking effect. So what we will do is display dot clear display. That's it. And now what we'll do is we will remove this and we will call process input and render. That's it. So just to recap, we created four buttons, left, right, up and down. We created a struct to better represent our player. We gave our player some initial properties. We created a function for processing the inputs where we check if any of the buttons are pressed and we update the player position accordingly. And while doing so, we also make sure the player is not going, or the object is not going out of this viewable or visible screen. And we create a function to render player on the screen. We make sure to clean up the screen before rendering the new updated positions, and we call these two functions from our main loop. So let's try to upload it and see if it compiles without any issue. Okay, so it's done, and let's see how it looks on the actual screen. Okay, so this is how our updated circuit looks like. We have introduced 4 new buttons, one for up, one for down, one for left, and one for right. Pretty much how it looks on a gamepad, but a very crude and raw version, right? And we have our tiny rectangle printed almost towards the center of the screen, and we have done similar connections. So now I've connected the grounds of all the buttons to the same ground as I mentioned earlier, and also I have connected that ground to one of the grounds of the pico. And now let's test it out. So if I press left, it goes left, but it hits the boundary and it doesn't move further. We can go right, and we can go up, and we can go down. So that's our tiny playable, or rather controllable game object on the screen. We are able to control using our physical switches. Cool. So now we have all the basic requirements for our console, and we know how to write code for the pico. We know how to upload it. We have our environment. We know how to access and draw things on the screen, which is SSD1306 I2C OLED display. We know how a button works, how to connect it to our Raspberry Pi Pico, how to capture button state, and we can also now create an interactable experience wherein we can use our buttons to control something on the screen. So I believe this is it for this video. In the next video, we will start working on our first game for this console, which is Space Invaders. Also, before beginning working on that, the other thing that I would like to do is change the structure of how this project is currently set up. Right now it's just one INO file, which is not very scalable and rather which is not very maintainable. So what I want to do is I want to create dedicated files for the different games. So maybe one source C file for Space Invader, one source C file for Pong. Both the game files will have, or both the game code source code files will have their individual header files, which will finally get imported into the monoretro.ino, and which is the entry point. Depending on what the player selects on the screen, we will use functions from the respected header file to control our game. So if someone selects Pong, then we will use the Pong header files to play the Pong game. Otherwise, we'll use Space Invader. But in the next video, we'll just try to set up different files for the games and introduce the header files. And yep, we'll start working on Space Invaders. So yeah, that's it for this video, and I hope you all enjoyed this. And so see you all in my next video.